Hi, this is Sonia Doucette. In this video, I'll show you how to find the Kn value for a neutralization reaction involving a strong acid and a weak base. And in order to find the Kn value for a neutralization reaction, you first need to identify the net ionic equation for that neutralization. What you're asked to do in this problem is to write the balanced net ionic equation for the neutralization reaction involving equal molar amounts of hydrobromic acid and ammonia. Calculate Kn for this neutralization reaction. The first thing you want to do with these types of problems is to identify the acid-base properties of the two substances involved in the neutralization reaction. First, we'll deal with ammonia, so NH3. You can find a Kb value for ammonia, and when you look that up in a table of base dissociation constants, you'll find you get 1.8 times 10 to the negative 5. A good rule of thumb here is that any base with a Kb value of less than 1 is a weak base, so we can consider ammonia to be a weak base. Other good rules of thumb to remember are the lists of the cations and anions that do not react appreciably with water. The cations that do not react appreciably with water come from strong bases, and those cations are lithium, sodium, potassium, magnesium, calcium, strontium, and barium. There are also anions that come from strong monoprotic acids that do not react appreciably with water and also do not participate in the acid-base chemistry. So those are chloride, bromide, and iodide coming from the group 7A halogens, and nitrate and chlorate are some polyatomic anions that do not react appreciably with water. If you look at what we're dealing with in the other component of this neutralization, we have hydrobromic acid, and hydrobromic acid, when dissolved in water, dissociates into protons and the bromide ion. So the proton will quickly react with a water molecule because it's very reactive, and you will get a hydronium ion. But if you look at the bromide ion, you can see that it's part of this list of anions that do not react appreciably with water, and you know that these anions come from strong acids. So we can say then that hydrobromic acid is a strong acid and ammonia is a weak base. Once we know this, you can realize that you're dealing with a strong acid, weak base type neutralization reaction. And that means you can use the generic form of the net ionic equation for this type of neutralization reaction. So for a strong acid, weak base neutralization reaction, the general form for the net ionic equation is the hydronium ion plus B, which represents the weak base, which is only partly dissociated, giving you water plus BH+, which represents the conjugate acid of that weak base. So making this specific to the net ionic equation for this problem, we keep the hydronium ion. So this ion comes from the strong acid when it dissociates. Our base, in this case, we've identified as NH3, so that's our weak base. We keep the water, and the conjugate acid of that weak base is NH4+, or ammonium. Now to find Kn, you have to multiply known equilibrium constants for reactions that add up to give this net ionic equation that we've just written here. For strong acid, weak base type neutralization reactions, there are usually two reactions with known equilibrium constants that we're interested in here. The first one is the reaction for proton transfer from water to the weak base. So our weak base is ammonia, and the proton will be transferred from water to that base to give you the ammonium conjugate acid of that weak base, and hydroxide. And we can look up the Kb value for this reaction, and it's equal to 1.8 times 10 to the negative 5. And in fact, we've already talked about this Kb value because we used it to identify ammonia as a weak base. The second reaction that is often used when you're dealing with strong acid weak base neutralizations to calculate that Kn value is the reaction for the neutralization between the hydronium ion that comes from the strong acid, so in this case hydrobromic acid, and the hydroxide that's left over when water transfers a proton to the weak base. So this hydroxide anion is the one we're talking about. So we have a neutralization between the hydronium and the hydroxide here. So that will give us hydronium ion plus hydroxide going to 2 water molecules, which is what's left over when the hydronium ion transfers a proton to the hydroxide ion. And the K value for this equation is 1 over Kw, which is equal to 1.0 times 10 to the 14th. So before multiplying these two K values together to get the Kn value for the overall neutralization reaction, we should check to make sure that the two reactions here add up to give the net ionic equation. In order to do that, you're going to want to cancel out species that appear on both sides of these two equations. So we can get rid of the hydroxide ion, which appears on both sides. We can get rid of one water molecule, and all the others appear on only one side of the equation. So we're left with the reactants as ammonia plus the hydronium ion going to ammonium, the conjugate acid of that weak base ammonia, and water. So you can see that we get that original net ionic equation that we wrote back again when we add the two together. So that means it's okay to add up the equilibrium constants for these two reactions to give us a Kn value for this net ionic equation that describes the neutralization reaction between the weak base ammonia and the strong acid hydrobromic acid. So the Kn value for that neutralization will be Kb times 1 over Kw. Substituting in the numbers, we get 1.8 times 10 to the negative 5 times 1.0 times 10 to the 14th for our 1 over Kw value. If you do the math here, you're left with 1.8 times 10 to the 9. So this is the Kn value for a neutralization reaction here, which was between a weak base and a strong acid.